In this video, we'll see that similar equations that we had for autocorrelation function, cross-correlation function, and so on for continuous time signals, we do have them for discrete time random process as well. So for digital processes, it's simply a random sequence xn, and the autocorrelation and autocovariance of x of n can be similarly defined, because if you take two samples at time n1 and at time n2, so the expected value of this product is called autocorrelation function. Here, if this function is only a function of the time difference n2 minus n1, then we call it we call this a random process stationary, provided that mean of x of n is also constant. So same definition, just the only difference here is that the time is an integer value as opposed to be any real value. So the autocovariance is just you remove the means. So similar definition can be easily defined for discrete random processes, so you could do this in a way. Similarly, you can define a secret sensor stationary and wide sensor stationary processes for discrete time random process. Same definitions could be applied. Even more, these digital processes, because the time instances are integer, is easier to manipulate them, because you are dealing with a random sequence as opposed to a random signal. So an LTI filter for discrete time signals, you could analyze them in Z domain instead of Laplace domain. So Z transform is defined for an LTI, so the Z transform. So the output of an LTI filter is defined by the convolution of your input random sequence or discrete time signal with this filter, which is defined by the convolution sum as opposed to convolution integral. And a similar result we have obtained for discrete time, continuous time signals. We can extend it for discrete time with the correlation function if they are wide sensor stationary. So similar theorems we had for the continuous time or jointly wide sensor stationary input and output and so on could be extended here with same results, and the autocorrelation function of the output is convolution of the sky with another times with this one. So remember that this x here is converted to this y, and because we put a conjugate on the second one, we have to convolve this function with a conjugate, and because here this applies on the second term, we have to put negative here in order to convert. So similarly, we could convert this x to this y by convolving with h of m. And if you put this guy in the second equation, we get the third equation, which is the autocorrelation function of the output is equal to the input autocorrelation convolved with this one. Obviously, you can apply Z transform and then get the power spectral density of this function. So Z transform of this random process is denoted by S y of z, and if you calculate is equal to S x of z, and Z transform of this is h of z, and Z transform of this is h conjugate of 1 over z conjugate.